Hello. That should work now. Good, very good. So the lecture will be about, well, it's yet another deviation from main topics, but everything kind of goes into the same lines. The lecture will be about quantum corrections. We have already started scattering approach. We have figured out the importance of GQ, conductance per quantum channel. We look at interference, at the distribution of transmission eigenvalues of these conductors. Now we want to explore the case when there are many transport channels, the case of large conductance and perhaps rather big sample. And we were going to zoom on corrections due to quantum mechanics, quantum corrections, right? I would say perhaps from very beginning that these corrections have order of magnitude of GQ, just one channel of many, right? There are corrections which survive in average weak localization. There are fluctuations which for some reasons are called universal conductance fluctuations. In many experiments, the best way to sort out these corrections is magnetic field dependence. Why is it so? You might remember the lecture about interference. Magnetic field penetrates the loops which electrons make. It makes a Aronoff-Bohm effect. So magnetic field essentially alters interference at some length scale. So from magnetic field dependence, one can experimentally see these quantum fluctuations. Fine, so we will try to quantify these effects. We will look at weak localization as return probability of the trajectories. And we also try to assess it from a different point of view, from a point of random matrices, right? So you might remember we have had matrices, scattering matrices to describe conductances. They're big because of many channels. We can look at transmission matrix, make a square of this, and look at it as a random matrix. That also gives us estimation of fluctuations, estimation of quantum effects. Very good. So let us see. What to observe and how to observe. Let us consider coherent classical conductor. So what is that about? What does it increase? There are many channels. That's why transport and this conductor is more or less classical. There's usual Ohm's law, for instance, if you connect these two conductors. But it is coherent which means that electrons propagate in this conductor still as waves. So quantum coherence is preserved. Right. And the point is, which I have already cited, that there is small interference contribution in these conductors, and this is of the order of 1 channel. Again, it's interference which can be tuned by magnetic field, so it is experimentally accessible if we measure conductance as a function of magnetic field. Yet it requires some precautions to keep this classical conductor coherent. We have shortly discussed it, and we will discuss this in detail in last lecture, in lecture number 12. But the point is that at very large scale, of course, the electrons are not coherent quantum mechanical waves. The subject of dissipation, the subject of decoherence, so they forget about its quantum nature. Ohm's law still holds, but it is for incoherent classical conductor. That's kind of first you saw, you think that makes it really unsolvable. You don't know how to treat it. The key ingredient is that this incoherence sets up at some length scale in directions which break, which spoils quantum mechanics. They're rather weak. It takes quite some time before they start working. And electrons fly long distance during this time. So the length at which a conductor becomes incoherent is rather long. And one can say that at this size, the conductor is coherent, and what we have as incoherent conductor is just a collection of small coherent conductors. And each coherent conductor still has interference contribution of that order. So this can be seen in both situations for coherent classical conductor and for incoherent one, if one takes into account that incoherent conductor is a large collection of coherent ones. Right. Why there is so much attention to this topic? First reason is perhaps historic. It's really how people began to understand that quantum mechanics can be seen not only at the level of atoms, and it's not only made to explain band structure or atomic structure, atomic physics, whatever, nuclear physics. It also has manifestations at macroscopic scale, at a scale of several microns. For instance, this incoherent conductor coherence in such situations can be kept at the scale of 10 microns. Right, that's what people in ETIS called mesoscopics. Perhaps you can still hear this word from time to time. What does it mean? They meant this very small scale, microscopic scales of the order of atoms, molecules. It would be like 0.1 nanometer. There are macroscopic scales, which are of human scale, meters, centimeters, millimeters. And there is some scale in between, meso, which is on the order of microns, 100 nanometers, where quantum mechanics still play a role. That's why so much attention has been given to research of these quantum corrections. And output of this research that they're very handy for material characterization, to see these effects in new structures, materials, devices, kind of make you sure that you understand those materials just by seeing these known effects. All right, what are the effects? What to look at? First effect is a weak localization. And it is convenient for me to define it rather mathematically as a correction to conductance, which is averaged over many formally identical nanostructures. Kind of, you make nanostructures, it's diffusion nanostructure, and you aim always at whatever 10 ohm in your structure. They become different because of different positions of atoms. They give you different interference patterns. There are fluctuations, but there's also average deviation from Ohm's law, from classical conductors, which is called weak localization. All right, making nanostructures, it's pretty much unpractical. It might require months. It is much less invasive way just to take sufficiently long conductor incoherent sample. Then, as we figured out, it can be separated into a large number of coherent nanostructures. Each nanostructure has its own correction to conductance. So let us see, if I look at the total conductance of the sample, it will also give a correction to conductance. Well, that will be inversely proportional to the number of elements in this geometry. But well, conductance can be measured with high precision, so it should not matter much. Fine, weak localization, average value. Here, I would tell a story about universal conductance fluctuations. So I have already mentioned that if you make these nanostructures, although they are formally identical, you can never shape it with the accuracy of atom to atom. So the conductance of formally identical samples fluctuate. Right, so we can again do this Gedanken experiment, produce many nanostructures and now compute the dispersion of their conductances, right? And that, again, the same message. It's of the order of weak localization correction. It's still of the order of one channel contribution, still of the order of GQ. Again, making the fabrication of many nanostructures is not very practical, and we better turn to big incoherent sample. All right. That's I explained how to compute the fluctuation of a big incoherent sample. In this case, it's fluctuation of resistance, but doesn't matter. So one can see fluctuations even in big samples, which of course will be sums of fluctuations in individual coherence, in individual coherent samples. Right. How to understand that it is fluctuation? I have already demonstrated such an experiment in lecture number 2 when we discuss Aronoff ring. There was very random dependence of conductance on magnetic field, which looked like grass. And that is the way to see and characterize these fluctuations. You change magnetic field, you change interference pattern, you can modulate these fluctuations by order of value. Fine, let me talk or whatever, remind you a bit about magnetic field dependence, because we have discussed it already in lecture number 2 as interference of trajectories which go through 2 beam splitters. All right, so electrons go through 2 beam splitters. They can take different trajectories. And each trajectory is a choice. It's like a slit there are many slits, but it's analogy with double slit experiment. So you sum up amplitudes for each trajectory for each slit. And it's not the same as you sum up probabilities. That would be classical. So we look at interference contributions, and there are very simple trajectories, A and B, and they provide universal conductance fluctuations. It's an origin of universal conductance fluctuations. Right, so they depend on what we call dynamical phase, on all peculiarities of nanostructure potential. Right, while there are special trajectories, and what is special in these trajectories, it is a presence of a loop. Let me outline it perhaps with some other color, yellow color. So here's a loop, and trajectories E and D, they are almost identical, but they differ in order the electron goes along the loop. So here it is, let us see, here it is anti-clockwise, and here it is clockwise, right? So if one considers the interference of these trajectories, the answer won't depend on dynamical phases, so it survives on average. It survives when we average over dynamical phases. All right, so we have shortly discussed it, but now we are going to discuss it for really big samples. Right, so let us understand that magnetic field also has an ability to do some microscopy, if you wish, the ability to concentrate on a certain spatial scale, right? One understands it from the fact that basically interference is maximal, is most effective when there is about 1 flux quantum in the interfering loop, right? So that sets space scale. At any given magnetic field, there is a space scale at which a typical flux in a trajectory is of the order of 1. That's the estimation. So just size of area covered by the trajectory times magnetic field, it's this flux. So one can introduce a lens which is a function of magnetic field. So if, and this lens can be compared with other lens scales. In our case, it's mostly with incoherence lens. Right, so change in magnetic field, one kind of assesses interference at different spatial scales. That's the message of this transparency. Oh yeah, I forgot to say that, right, if one knows how electrons move, and in large samples, they mostly move diffusively. In the samples of big conductance, they mostly move diffusively. Right, there is a relation between the time and length given by diffusion law, given by diffusion coefficient. So one can also introduce typical time scale related to magnetic field. Let us see, and now I'm gonna repeat something which I told you in lecture number 2, and introduce some new experiments. Right, let us recall that old stuff, really very old. First pioneering experiment, and they see Aronov-Bohm interference in macroscopic, it's not micro, it's not very macro, it's mesoscopic sample, which was a rather long cylinder, like 1 millimeter, so it can be macroscopic, but which has been has been evaporated on a very thin crystal whisker. So the opening was something like 0.3 micrometer, something like that, if I remember precisely. So there was the full conductance of the sample, which has been measured just by imposing contacts on it. And there was an interference contribution, which was pretty small. I don't have absolute value of resistance in this plot, but I would guess it was about 100 ohms. So it was like 10 to the minus 3, 10 to the minus 4 relative change of conductance. Oh, still traceable. Again, conductance you can measure with very high precision. Right, as a function of magnetic field, and there was a period corresponding to flux quantum penetrating the cylinder. Okay. The same phenomena, the same weak localization can be also seen in different circumstances, which is illustrated by this plot. In this case, they have two-dimensional gas, some semiconductor heterostructure, and it was really a large sample, perhaps inch by inch. They measured its conductance as a function of magnetic field. They also had gate ground plane below the two-dimensional, below the plane of two-dimensional gas. Changing gate voltage, and it was really sensible change. Like, yeah, you can see it here, 100 millivolts. Right, they could change the properties of this two-dimensional gas. So as you see, the caves a bit different, right? So some of them, eventually all of them, display a peak, but for some of them, they also see very pronounced dip at larger magnetic fields. All right, and this effect is also due to weak localization. We will explain it a little bit more detail when we kind of have more quantitative theory of this phenomenon. Let us see. Eventually, I go pretty fast. Have you noticed? If I go too fast, please slow me down, because I really very scared by the fact that we have started it with delay. Perhaps I go too fast without recognizing this. Weak localization. It is can be done regularly in many structures. From experimental point of view, you just need to go to low temperatures, of course, otherwise all coherence will be broken. And measure magnetoresistance, as you see, at pretty small magnetic fields. And that is how to measure weak localization. Good. Again, it is the same experiment which I repeat. I didn't have to concentrate on the same experiment because eventually in any metallic superconducting nanostructure, one can see the same patterns, right? Some irregular magnetic field dependence. So here they have a loop, and there was right. If I look at magnetic field which corresponds to flux per loop, it will be something like that. But one can see that magnetic field dependence also is seen as a smaller scale, corresponding to more to longer trajectories, which means that there are many windings along the loop. So, well, whatever, it's rather random dependence. They make a spectrum of this dependence. They made Fourier transform with respect to inverse magnetic field, and they can see the peaks related to the flux in the loop. All right, so it's very a general phenomenon. Suppose we don't have a loop, but still see this random magnetic field dependence. I want you to tell me which space scale and space scale we can immediately revert into magnetic field, right? At which space scale we are going to see these fluctuations. So here geometry is rather given. It is, they made a loop. Suppose you don't do this, suppose you just make it, okay, I need a black color. You just make a sample like this, all back. And you still see the random magnetic trace like this. So what will determine the period in magnetic field? That has to be interference of trajectories of certain size. And there are basically two choices. Let's have these two choices.
They have to be larger than the LH that we mentioned before with the weak localization.
LH is something which is a function of magnetic field, right? So if you change magnetic field, you kind of change the visibility of trajectories, interference of trajectories at different space scales, right? So here the visibility was, space scale was set by geometry. So how about this situation? Just square sample. Think of space scales which do not have anything to do with magnetic field. Magnetic field is just a mean experimental tool to figure out what are these scales. Scattering lengths within the, or that could be, but that will require, scattering length is very short, it's mean free path. It can be like 10 nanometers in most materials. Practical materials, it's pretty short. In principle, yes, but in this case, the whole resistance will be affected because scattering of electrons will be affected as holes, also classical scattering. The trajectories which just go in magnetic field like this. It's not interference, just real bending of trajectories, right? I don't mean anything fancy. First of all, there is a scale which is just the size of the structure. Okay? There can be no trajectories which are larger than this size. But there is another scale which I didn't tell much, but I mentioned it several times. I've been talking about coherent conductors and incoherent conductors. So there used to be some scale, coherence length, which separates. So we have to choose this as a size of the conductor or incoherent length. Depending on temperature, because temperature changes in coherence length, we could be in the situation where either one scale dominates or another scale. So in one case, if at very low temperatures, this is larger than the size of the conductor, it can be coherent, right? Then we see magnetic field patterns at this case of L. But it can be at high temperature, we switch to this scale. Good. Right, that's understand the qualitative physics about this. I want to tell you something. I would not normally tell this to students, but it's really very, experimentally, it is really a rather interesting signature in weak localization, what makes it really so fancy. So I would tell you a bit about anti-localization. All right. First of all, what is called localization. So usually this correction to this conductance is small. It's negative correction, so it makes the total conductance smaller. However, if spin is involved in the scattering of electrons, it could give rise to positive correction. So to have a toy model for this, I consider interference of two trajectories. So I have amplitudes corresponding to these trajectories. And I also want to make the spin part of wave function to change along the trajectory. Normally it should not happen, but the spin orbit interaction, and if you have it, if you move spin, you also, if you move an electron, you also change the direction of its spin. With this, each amplitude will become a matrix which has spin independent part and spin dependent part. So I might just take two trajectories for simplicity. I take it with the same spin independent amplitude and opposite spin dependent amplitudes. Then I take these trajectories, I interfere them for both directions of spin. So what I like to know is look at electric current. It doesn't matter which spin is involved, so I sum up over spin. All right, I see that if I look at classical effect, that both spin dependent and spin independent part, they come with the same sign. But if I look at interference contribution, they come with different signs. That's why if spin orbit scattering is small, we expect localization. But if spin scattering is big, we might expect anti-localization, change of sign of correction to the conductance. Okay, now I want to sketch how people first treated this weak localization quantitatively. Is it time for a break? Do you feel like breaking? Okay, let's have a 7-minute break. No, let's see, 8-minute break. So weak localization and return probabilities. People at some stage made a rather simple but very challenging calculation, very bright calculation. what they wanted to understand. They want to find the correction which is affected by interference, by weak localization. And they decided to look at the relative size of this correction, divided it by classical conductance. And they got the idea that this ratio is in fact the ratio of trajectories with loops, which I mentioned. Okay, there's a loop which can be traversed into opposite directions that gives rise to interference, which doesn't depend on dynamical phase, right? So the number of trajectories with loops and without loops. Good. If you treat this problem mathematically, if you consider random trajectories of infinitesimally small width, then this ratio, of course, will be 0. It has to be because this correction is a quantum effect, and how quantum effects would manifest itself in classical trajectories. Quantum particle cannot just take infinitesimally thin trajectory. Rather, it will propagate in a packet which will have at least a size of the wavelengths. So you cannot, if you have a wave, you cannot make it more narrow than its wavelengths. Good. So the problem is reduced to finding intersections of trajectories of finite width. That's good, and that gives a factor which is density of states. Next to it, and this is a crucial point in understanding, is that the number of loops for a trajectory of a given length, or which is the same given time of propagation, is just given by probability for a classical electron to get back for this time. Classical return probability. All right. So we are looking at closed loops, which are closed within a given time. And to that, we just need to have classical probability to get to the same point during time t. Fine. So there are loops that are of different size. All of them take part in this interference. So I just sum up, I integrate over t. It means that I sum up over loops of different size. Okay. Then I need to add some time-dependent factors. This factor accounts for decoherence. It means that some sufficiently long trajectories alone as at time tau f do not contribute to interference. Okay, so exponentially small exponential factor which makes a contribution of these trajectories to vanish, provided this time is exceeded. Magnetic field gives also a very similar factor, but in this case we have tau h, which depends on magnetic field. We have evaluated it. It corresponds to time where area is affected, where magnetic flux can go in, a quant of magnetic flux. Fine. Now I have a little bit more story to tell. It's anti-localization correction. It comes from the treatment of spin. There is some length at which spin changes sign. It is spin localization, spin orbit length, which shows how spin scattering is effective. And that also, for anti-localization, kills the effect, but localization remains. Localization remains, negative correction remains, because yes, it's survives at for trajectories which are longer than spin orbit lengths. Good, so there are three space or time scales involved. Two are more or less fixed at the given temperature, at least in dephasing time and spin orbit time, and magnetic field can change. Right. As to probability, that probability, it is a classical problem about diffusion. It is to understand how electrons or any other diffusive particles would propagate from a point-like source. Or you just fix position of particle or just put it by your hand, you see how does it propagate. Qualitatively, it is clear. What does it do? So you start here, you go the random trajectory, more time, you have more spread you have for the trajectory. But from time to time, this trajectory comes back to initial point or comes very close to it. So this gives you return probability. This probability also drops with increase in time because an average particle goes farther and farther from initial point. Okay, let us have a simple estimation, eventually just to show that, I guess I don't have important formula this slide. Never mind, what I wanted to tell is a following estimation which shows that the ratio of the conductances is what we assumed from very beginning. Let us consider a structure of a given volume. Then what's a particle would do, which we put it, okay, it will diffuse, it will spread over the volume, then it will go away. Return probability would be of the order of inverse volume for a time interval. Let's call it dwell time. It would be just escape rate from this piece of material. Right. In the definition of this formula, of this correction, we find density of states. That comes from finite width of trajectories. It also enters here. So after the estimation, we have 1 over volume, density of states, and this is, this comes to level spacing. And we have to compare level spacing and escape rate from this piece of material. And that's gonna be conductance in terms of conductance quantum. Why is it so? Let me have a simple cartoon. Let me have this piece of material with levels separated by delta S, and these levels are all filled. And let me take another piece and shift it a little bit in voltage. So electrons in this energy strip will go to the left and produce a current. So how many electrons will go per second? Escape rate times number of levels in this energy strip. All right. That's number of levels, width of energy strip divided by level separation. And that's gonna be current divided by E. From the other hand, current divided by E is just voltage time conductance divided by E. I guess I missed H. bar somewhere. I guess here. Right. With this, it will become correct estimation. And now we see that it is all consistent. It corresponds to what I told you in the beginning of this lecture. Right, here the result for 2 dimensions. So it's experimental situation we looked upon, very large 2-dimensional gas, large meaning it's a macroscopic scale. And this is the answer. All right. It is the solution for return to probability in 2 dimensions. As I promised, return probability goes down with increasing time. And at average, the starting part, the particle has gone far from the origin, so the probability still come back goes down with increasing time. Good. So one puts it there on the integration time. So typical integrals are of this kind. Those are log integrals. Okay, and I take all these log integrals and I have to cut them at very short time tau. And all three time scales, incoherence, spin orbit, and magnetic field dependent time scale, they all come into this formula. This is the formula for the correction. And now I can come to the experiment. Good. So what does it show? The dip and the peak are manifestations of weak localization and localization and anti-localization. And it appears to be that what we change with gate voltage is the strength of spin orbit interaction. And if spin orbit is smaller than dephasing, then we expect a deep localization. For bigger SO, we expect a peak, and indeed we see the peak emerging if you change gate voltage, you make spin orbit configuration bigger. How to quantify the spin orbit length? Okay, you still measure it versus magnetic field. And you see that at some magnetic field, you have a wiggle where deep it goes to peak. You have these things. I better take another color. It's not very well defined because there's no anti-localization. Let me put it somewhere here. Fine. At this point, all three scales are of the same magnitude. So one can measure spin orbit scale as a function of magnetic field. From the magnetic field corresponding to these peculiarities. Fine, so we can, yes, and the feed to the experiment are the formulas which I demonstrated. As you see, the fit is not very perfect, but yeah, at least it gives you a good idea of what's going on. Right, that's weak localization that has started as a challenging set of experiments to demonstrate that quantum mechanics works at any scale, not only at atomic scale. And now it is used for characterization of nanostructures, different materials, and just to check that one can see familiar effects in these structures. Good. Then let me switch gears in a very drastic way. Let me talk about random matrices. Hamiltonian is a fact, a random matrix. One can say it is a physical realization of a mathematical concept of random matrix. What do we have in a Hamiltonian? We have energy levels. If you ever tried to determine eigenvalues of the matrix, whatever energy levels of Hamiltonian, you understand that at least you would have to make an equation for determinant. And in order to know the determinant, you eventually have to check all elements of this density matrix. So if elements of this density matrix are independent, you cannot say that, for instance, eigenvalues are independent. Would be very emotionally attractive thing to say. You just don't have to think much. But in fact, they do know about each other. Matrix elements do not. They're just random values. But the levels, they care about each other. These gentlemen, Wigner and Dyson, have figured out the statistics of these energy levels. How did it come about? They have been employed in atomic projects in the United States of America. They've been studying different nuclei. It was very important practical problem by the time, so they've been overwhelmed with information about thousands and thousands of experiments with many thousand nuclei. It was a really very big database even by that time, big data. And they got bored with that. You cannot find any sense in big data. There's so many various information. And I say they've been kind of rioting in a scientific way. They say, we cannot know anything about this nuclei. Let us just assume that the Hamiltonian which governs nuclear structure is random. Good. And they could explain all this big data in one step. Of course, in this way, you cannot get prediction for each concrete nucleus under consideration, but at least you understand understand this big data. So, how do they correlate? What I write here is a probability to have certain realization of the eigenvalues. In our case, many eigenvalues, right? And there are two large factors in this probability. First factor forbids the levels to be the same, to be at the same point. One can say it's a repulsion of the levels. It has repulsion, so this probability is always zero if two level coincides, like it can happen. That comes with some power. I will tell you a little bit later about. And look, if the levels are particles and they repel, they would like to take the whole axis, go from infinity to minus infinity. There must be something which confines these levels. So the second factor is confining these levels. So you have larger probability to be at zero, but due to repulsion, the levels cannot be close to zero, right? So one could introduce a physical model. It's a model of charges which are subject to thermal fluctuations, which are in parabolic confining potential, and which repel each other by logarithmic law. Why logarithmic? Well, a Boltzmann factor is kind of exponent of the energy. So if repulsion energy is logarithmic, it corresponds to these factors. So it looks like a gas of particles with logarithmic repulsion in a confined potential. Z beta looks like inverse temperature in this model. If temperature is zero, these particles would form a rather regular lattice. So you would say something like that. If temperature is very high, then the positions of the particles would be rather disordered. Perhaps a situation like this. This temperature, and that's a kind of a rather unusual conclusion of random matrix theory, can take only 3 values, which depends on symmetry or ensemble of the matrix. So the matrix can be just Hermitian matrix, and that corresponds to unitary ensemble. If there is no magnetic field, the matrix and the Hamiltonian is symmetric. It's a real matrix, and it corresponds to orthogonal ensemble. And if spin orbit is strong, we have already heard that spin orbit is of importance. So here, it's another ensemble is symplectic. Here, I just put the systems of levels of the particles corresponding to different ensembles. Please look attentively here. So P corresponds to random levels. They just don't know each other, and you see sometimes they can come very close, almost overlapping. So complete disorder of the levels. Here it's orthogonal, and you see that the levels become more ordered. Here unitary, so the temperature goes lower. Here it's symplectic, and if you just look up at symplectic ensemble, you see that the levels are, well, if you don't look carefully, they look almost equally spaced. All right, so it shows that the strengths of correlations in this spectrum, strengths of level repulsion in random matrix theory. What's important for me is a concept of spectral rigidity. Did I tell more about this? No. If one just takes random levels and compute the number of these levels in a strip where you have n levels in average, then variation of this number, so the fluctuation squared, will be of the order of n. Poisson distributions. That's usual, that's what we're accustomed for in random processes. That's basic thing of every measurement. You have to repeat measurement many times to increase accuracy. But that does not work for disordered spectrum of random matrices. In this case, variance is not proportional to the width of the strip. Variance does not depend on the strip. So if you have a strip where n levels are situated, the fluctuation is of the order of 1. Okay, well, it depends on temperature and this random matrix ensemble parameter. Let's see, I'm doing on time. Okay, so have to go fast, but basically to apply it to our situation, one just has to find a proper matrix. So in our case, it will be squared of transmission matrix. We look at it, we understood that important are eigenvalues of this matrix, set of transmission coefficients. We look at this distribution, right? Let us look at the distribution for a nanostructure, which for which we can compute this distribution explicitly. It's something which we look upon. It's a chaotic cavity, two quantum point contacts connected in parallel, and the node between them is this cavity. Then we look at it, distribution, and we find the typical features of random matrix theory. Level repulsion for these transmission coefficients. And that sets a confinement. In this case, the confinement looks a bit different because all these coefficients have to be confined to the interval from 0 to 1. Those are transmission coefficients. Right, so one can write it as logarithmic repulsion of the levels. Fine. Now we can go to conductance fluctuations, and we define the conductance with Landauer formula. So the variance is this variance. How one can get it simpler. So conductance is in fact a number of eigenvalues in a strip of the order of 1. How many eigenvalues have transmission of the order of 1? So the variance of conductance is a variance of number of levels in this strip. But again, random matrices dictate that it is of the order of 1. If we would forget about the fact that conductance comes from scattering and can be described as a big random matrix. If you would just say, oh, we just have n independent channels and they fluctuate somehow. If channels were independent, the variance would be proportional to the number of channels. So we would immediately predict something like that. Which is not true, which is much bigger than the actual fluctuation. So again, it is, the way I put it, is a direct manifestation of quantum mechanics. It means that there is a large matrix involved behind, large matrix is behind this big number of channels, which provides spectral rigidity. Let's see, it's for weak localization, and eventually what is important here is that weak localization vanishes in magnetic fields, but that we also see, we have also seen that in experiment. Right, one can make concrete calculations for, again, for chaotic cavity. One sees that, yeah, it is called universal fluctuations, but it's not quite universal. Universality, it means that they are of the order of conductance quantum. There was a time when people thought that these fluctuations are universal, not depending on the shape of the sample, on properties of conductors which compose the sample. That appears to be not true, but here it's illustrated by the fact that variance does depend on both conductances of both point contacts. Fine, what I want to mention in remaining minutes is how weak, localization becomes strong. Or in other words, how quantum corrections, which are small, of the over GQ become bigger. In a way I put it, it looks evident, but the better way is to think of conductance of a lone one-dimensional wire. Its classical conductance is inversely proportional to the wire length. Ponder it for a second. Do you understand this, sir? Resistance is proportional to the length. Conductance is inversely proportional to the length. All right. If you're talking about usual method, then electrons scatter, but they still propagate through the whole sample. They're not very much, they're not localized. Another situation which you can encounter is a situation of quantum dot, where electrons are localized, for instance, between two potential barriers. Right? And in this case, conductance must be smaller or of the order of this GQ. And now what I want to say, if you just start with a one-dimensional wire, which is pretty much normal, usual metal, is the localized wave functions, and you make it longer and longer, simultaneously making temperature lower and lower, right, to keep it coherent. Then you encounter these quantum dots in this pretty innocent one-dimensional wire. How come? If the wire is sufficiently long, its conductance will become of the order of conductance quantum. It will become of the order of conductance quantum. Interference will become important. Scattering will become important. So there will be less than one conducting channel. So electron wave functions will get localized inside the wire. If I plot the actual conductance of the wire versus classical prediction, at longer wires, at large conductances, I will have only small deviation, weak localization, as we computed, of the order of GQ. If Y gets longer and longer, conductance goes smaller and smaller, and at some moment it becomes really exponentially small, corresponding to strong one-dimensional localization. So it is one of nice stories about localization. I guess I could skip it in, I could only say it is not that drastic in 2 and 3 dimensions. Good, with this, let me bring my apologies again for delayed start of this lecture. I hope I will remember it for the next lecture. And I guess we will have, so in one of the lectures, I don't remember whether it's on next week or next week, I won't be here. So anyway, you are invited to Zoom session. I will post an announcement already. And on coming Tuesday, there will be homework explanation. Is it also in this room? I guess so. Good. I will have to check it.
Did you already upload the homework?
Hmm?
You did not yet upload the second sheet. I didn't see the.
I was under impression that I uploaded all homework.
Okay, so I mistaken. Sorry.
But perhaps I'm wrong. If you could quickly check.